my God.
Okay, so before we get to the outline of the presentation, I just wanted to highlight that the Coxwell Bypass Tunnel is for Toronto Water, and it's being delivered by Toronto's Engineering and Construction Services, whereas the construction management team is Black & Veatch in association with RV Anderson, or RVA. I'm just RVA's PM. I'm part of a huge team, both in the office and in the field, to keep this project running. And some of the specialized team members for the construction management include environmental engineering, geotechnical, noise vibration, topographical. These are just some of the services that we're using right now. And the contractor is North Toronto Constructors, which is we call them NTC. And that's a joint venture between JD Canada, C&M McNally, and Michaels. And some of their specialized team include those listed here. So, you know, it goes without saying that there's a lot of people on this big team who know a heck of a lot more than I do, but I'll do my best to present some of these interesting details and answer any of your questions. And I guess I should say, I can't see the chat right now. I don't know where it is. There it is. I'm trying to pop that out. But I guess if there's any questions, we can either take them at the end, or maybe I can try and answer them as I go. Okay, so let's continue. All right, so this is the outline. We're going to talk about the Don River and Central Waterfront Wet Weather Flow Project. That's what those weird letters were at the beginning. Then we'll go into design, talk about the geotech investigation, hydraulics, tunnel design, shaft design, and the precast tunnel lining. And then we'll talk about a brief construction update. So we'll talk about where the shafts are, starter tail tunnels, the excavated tunnel, and the TBM, and then looking ahead for this project. Okay, so the Don River and Central Waterfront Wet Weather Flow Project. This is a big timeline here, and we'll come back to it a few times. But the first item is in 1987, an international joint commission designated the City of Toronto, or the City of Toronto's waterfront, as an area of concern in the Great Lakes Basin. And Toronto was just one of 40 areas given this designation. Well, how did this happen? Well, it's largely due to degraded environmental conditions in the lower Don River and along Toronto's inner harbor. Well, the degraded conditions are a result of storm sewer and combined sewer overflow discharges, which are released from outfalls into Toronto's waterways after heavy rainfalls or snowmelts. Now, how does that happen? Well, nearly a quarter of the city's sewer system, much of which was built a century ago, has combined sewers. And this is where there's only one pipe to carry both sewage and stormwater. Most of the time, combined sewers carry all the contents without much issue to the sewage treatment facility. In general, you don't really want to be treating, you know, a huge amount of rainwater and snow melt, but you know, that's what happens. However, during periods of really heavy rainfall, combined sewers may fill beyond capacity. And in this case, some of the combined sewers are going to overflow into creeks, rivers, and the lake. So CSOs, combined sewer overflows, they were designed to act as a relief valve to prevent sewers from overloading, you know, basement flooding and the sewer treatment system. So if you can capture these CSOs before it discharges into the Don River, Taylor Massey Creek, and the inner harbor, you can really significantly improve the water quality. So how do you capture this overflow during heavy rainfall events? Let's go back to this timeline. In 2003, City Council approved the development of the Wet Weather Flow Master Plan. And in 2012, the DRCW, Don River Central Waterfront EA, was completed. And then in 2014, Black & Veatch, in association with RVA, began pre-design of the preferred solution from the EA. And for context, this shows the sewer shed tributary to the Ash Bridges Bay treatment plant at the very bottom there, which was studied for the EA. Another image here just kind of shows the different areas and what trunks, you know, pick the flow up. But I guess the most notable feature here is the this single red line. It's called the Coxwell trunk sewer, right? So this red line carries pretty much everything you see here down to Ashbridges Bay. And there's no real redundancy to that line, at least not yet. So to give you an idea how big that area is that goes to Ashbridges Bay, looks like this. So anyone familiar with Toronto knows that's a pretty big area. It's 1.2 million served, 267 square kilometers, and 30% of this system is combined sewers. So the objectives of this overall Don River Central Waterfront Wet Weather Flow program is to improve the water quality in the Inner Harbor, Don River, Taylor Massey, and to delist them as an area of concern in the Great Lakes Basin. And to ensure future capacity of the system, we need redundancy to the Coxwell Sanitary Trunk Sewer. And of course, as we start implementing these multiple stages of the project, they help establish frameworks for the next stage and the next stage. And it kind of helps move this thing along. So let's talk about the EA, what the EA developed and where we are now. So there's 5 stages. Stage 1 is it's the Inner Harbor East Tunnel on the right, and the Lower Don, or the Coxwell Bypass Tunnel, up here. This big C, we just call this the Coxwell Bypass because it bypasses that single red line that I haven't drawn here that starts at this shaft up here, CX1A, all the way down to Ashbridges Bay. It's a bypass. And we'll get into more about all the details of this tunnel, but just kind of gives you a bit of a summary. Now, the idea here, we said, was to store CSOs, and the storage capacity of this tunnel and shafts is 550,000 cubic meters. And we'll talk about it later, but just so you know, this is a fully deep rock tunnel. Stage 2, the Taylor Massey Creek Tunnel, is it's a shallow soft ground tunnel, and it starts at this shaft, so they're all going to be connected eventually. Now this one is 93,000 cubic meters, and part of stage 2, at least, which was developed in the pre-design, was to also go ahead and construct all the outfall connections to the tunnel. I'll tell you later about some of the other connections. Stage 3, we're not really going to talk about today. It's a bunch of offline storage tanks way north of here, but the idea is to have 4 dry weather tanks and 3 wet weather flow tanks to help capture flows and store them so that you can prevent surcharging during a 1-year design event. Stage 4 is the Inner Harbor West Tunnel. Again, all these 3 tunnels are connected. This forms, if you will, the backbone of the Don River Central Waterfront project. And this one starts right next to this shaft at the Keating Rail Yard and goes all the way to Western Beaches. Now there's an existing shaft right at Western Beaches, so there will be another connection there to tie this whole system all together in a nice way. But then there's the final stage, stage 5. So I'll just go back first. So this is 1, 2, 3, 4. As we go to stage 5, you can see all these little, I guess, H's in Google Earth. These are the outfalls. This is where the actual outfalls are into the Inner Harbor, into the Don River, and then up here, the Taylor Massey. Each one of these outfalls will eventually be connected to the tunnels. That way they're not overflowing into the rivers. They basically go right into the tunnel. And once the storm surge event has subsided, it can all flow down to Ashbridges Bay. All of these flow down all the way to Ashbridges Bay, and it can be treated. So this entire project here is 22 kilometers of tunnel, 12 shafts, 27 connections into the tunnel, 7 offline storage tanks. The EA also called for a high rate treatment facility to treat the flows, an integrated pumping station, and it's expected to cost about $3 billion. So I realize now that I'm actually not able to see the chat. So if you guys are asking questions in the chat, I probably won't be responding during the presentation. I'm sorry. All right, so that's kind of the overview of the Don River Central Waterfront Wet Weather Flow Program. Now we all know what that acronym stands for. So let's get into design. Let's talk about the geotech investigation. So I was fortunate to manage the geotech investigation, which was intended to gather detailed design geotech for all 5 stages that I just showed you. And the intention of getting as much detailed design geotech as you can is to be as shovel ready as possible, so that when funding became available, they could just jump right on it. And we know that geotech tends to take a little while to get, so why not get as much as you can? So this is a plan and profile view of the Inner Harbor West Tunnel developed for the EA, just pulling this up to show you what information we started with. A major deliverable of the Geotech program was to refine these plan and profile drawings by filling in any gaps. So there were a few boreholes done here and there, but we really needed to better define the top of rock, which helps determine the elevation of your tunnel. And we needed to find, hopefully, any buried valleys that existed. We knew a few existed in a few places, such as the Don River, but we really needed to pinpoint those. And going to the next slide, this is the inner harbor, the lower Don tunnel. This is another cross section showing kind of where we thought the top of rock was, at least when the EA was done. And as you can see, it varies, it's up and down, up and down. And the Don Valley, the Don River is not straight as it looks. It was once kind of undulating up and down, and it was straightened. So we know that there are buried valleys in this area. So it was really important for us to delineate that. Also, we know that the rock is gray shale of the Georgian Bay Formation. It's pretty generally thinly bedded. It's a weak rock with a low hydraulic conductivity. It's got a lot of hard interbeds of limestone and siltstone. And the overburden is just a complex distribution of glacial till separated by sands and silts and clays. Now, this material is pretty well understood by kind of the local people and contractors who do tunnels, but that doesn't really matter. We really needed to confirm all of our past knowledge and document any site-specific conditions. And finally, the other tunnel, the Taylor Massey, this just shows you how or why it's in soft ground. The rock kind of comes up here, but then it dips way, way down below. And there really wasn't any need for it to be lower. And considering it had to drain into the Coxwell Bypass, and this invert was kind of locked, it just ended up being a soft ground tunnel. And the EA gave us 3 boreholes in this area. And for a soft ground tunnel, you need a little bit more than 3. So we'll talk a little bit later about the number of boreholes we did and why. I guess we'll talk about it right now. So the target borehole spacing for a rock tunnel, it varies depending on where you are and the type of material that you know is the bedrock. But in this case, the team decided to do 300-meter spacings. And typically you would want to put your boreholes about 2 tunnel diameters below the invert. That's just kind of good practice, but also if you need to change your invert, you're not going back and redoing your whole geotech program. For a soft ground tunnel, most of this tunnel was in kind of parkland, very far from any structures. So something like the Eglinton Crosstown, you'd probably want to put boreholes a bit tighter, and there's lots of buildings everywhere and you have stations all over the place. But in this case, 100 meters was more than enough. And if you find rock anywhere, you definitely want to quantify it properly. It could just be a boulder and you might have only gone into it a foot. So you want to go at least 3 meters in just to make sure that it actually is rock and you've quantified the extent of the weathered zone. And in general, this note here, you don't want your boreholes to be directly on top of your tunnel alignment. That, you know, if somebody decommissions the borehole and leaves, say, a big metal piece in there and your tunnel boring machine hits it, that could be a problem. So it's best practice to keep the boreholes a little bit off center from the tunnel alignment, at least as best you can. For shafts, and we'll get into the details of these shafts later, most of them are between 20 and 22 meter diameters. You know, the minimum, you definitely want to get 1 borehole inside the shaft. It's better to get 1 on either side of it if possible, because the rock can vary over 20 meters, that's for sure. And, you know, 1 data point doesn't constitute a trend either for the overburden quality. So you would typically want to do 1 deep rock borehole at least to the bottom and probably go 1.5 times the diameter of the shaft below. And then maybe a top of rock borehole again to capture the variation of the rock across the shaft and just to get a little bit more about the overburden. Anyone who's run a Geotech program knows your typical field activities include, you know, supervision, SPT, thin wall samples and certain types of materials, groundwater sampling, decommissioning, all the good stuff. But for this project, we did some more specialized things, such as in situ stress testing. We did borehole imaging for the entire extent of rock. Packer testing, which helps you determine the hydraulic conductivity of the rock, slug testing, the hydraulic conductivity of the soil. And we did some geophysical surveying as well, which I'll get into a little bit later. In general, we did 250 boreholes with 6.2 kilometers of vertical soil drilling, 3.2 kilometers of vertical deep rock drilling, and 1 kilometer of inclined deep rock drilling with over 175 monitoring wells. So the reason this is in red is because I want to highlight it a bit. It's not super standard for tunnel projects, so I want to talk about it a little bit. Now the bedrock in the GTA has locked in horizontal stresses. which came from the immense pressure exerted on the rock from the glaciers that once sat on them like 10,000 years ago. And that locked-in stress is still there. So one way to calculate that stress is by a method called overcoring. And this determines the major and minor principal stresses, which are orthogonal. And the method starts with determining the depth at which you want to do the test. So if your tunnel's at 50 meters deep, you probably want to do a test at the invert and the obvert and the spring line. So you drill an HQ size hole, which is 96 millimeters in diameter. Then you drill another smaller hole inside of it, an EX size hole. And you put inside of it what's called a USBM gauge. Then you overcore beyond that gauge. And what that does is it allows this rock here to effectively relieve its stress and deform into this open space. And when it does that, this gauge can measure the amount of movement. And you can use that to help calculate what stress is in the rock. So that's what the gauge looks like. And those buttons there, those are the buttons that get pushed in when it gets put into the hole. And those buttons can move. So as the rock wants to relieve its stress, those buttons can record that movement. Your typical data acquisition. And this is what it looks like. I'm not going to go into it in too much detail because this is a long presentation, but suffice to say that on the bottom here is the overcore distance. So once it hits the buttons, this is overcoring. Like, so let me just go back. So that would be the distance from here down to there. So as it's starting, it's just doing its normal thing. The buttons aren't recording anything. You get your normal noise. And then as soon as the overcore passes the buttons, you can see the rock starts to relieve its stress. And eventually it stabilizes. Sometimes tests are harder to achieve. Successful tests are hard to achieve. This isn't a guarantee because it's 50 meters deep, so it's not easy. But if you get enough tests, you can start looking at trends in your data. And what you do is you extract that core and do a biaxial test. And as soon as you plot that data, your displacement versus your pressure, you can calculate the elastic modulus, and you can help determine a bunch of other fancy parameters. So for those who are super nerds for geotech and love this stuff, I thought I'd put some interesting data up here. I would highly suggest you gather your own data for your project, but this is what we gathered from just the general program that we did. And you can see that some of the values here are pretty consistent with past knowledge for major and minor stresses. So that was nice to see. And the elastic modulus, again, was very, very similar. So even if you spend a lot of time and money on a geotech program, even if you've only proven that it is what you thought it was, that's pretty useful. Also, we did GIS survey, two different types. One is called seismic refraction, and another is called electroresistivity imaging. And the purpose of this is to help fill the gaps between boreholes. So this on the right here, ERI, you can see a borehole there and a borehole there. And the top of rock is denoted by that little red notch here and here. So for ERI, well, let's start with seismic. Seismic, basically you put a bunch of monitoring devices on the ground and you drop a hammer and you kind of can record the reverberation as it bounces off the shale. And for ERI, doing something similar, but with electricity, there's benefits to both of these, but there's also downsides to both of them. For example, if you're using seismic refraction, it's going to be influenced by construction nearby. If you got a lot of big drill rigs right next to your site, it might not be recording where your shale is. And if ERI, if there's tons of utilities buried, it's going to be bouncing off of that or being influenced by it. Purpose of doing these is to fill the gaps between boreholes that you've already drilled, but you need to be cautious because if it turns out that there are interferences either from buried utilities or nearby construction, you might not be getting the kind of useful information. But if you do happen to find a suspected buried valley in between your boreholes, at least you can go back and do supplemental investigation to look for it. All right, and in terms of laboratory tests, we did the usual geotechnical stuff, which helps with design, and the geoenvironmental stuff, which helps with determining, where the material may go once it's excavated, whether it can be beneficially reused or needs to be disposed of at a licensed landfill. And I'd like to highlight one specific thing. I don't have a lot of time to talk about it because there's a lot to talk about in this presentation, but we did some very interesting types of tests called swell testing, which is done by Dr. K.Y. Lowe from Western University. It's done by others, but that's kind of where it started. And the idea there is this rock, the Georgian Bay Formation, it actually swells upon stress relief and exposure to fresh water. And when it does that, it can actually put stresses on your tunnel depending on the methodology you use to construct your tunnel. So in this case, we did 180 swell tests of various types: vertical, horizontal, free swell, null swell. And that really, really helped the geotech program with the decision of the types of designs that I'm going to present in a few minutes. So just closing up quick, we did 6 different phases. 1 went to Golder, number 2 went to AMEC, who's now Wood. Phase 3 went to TerraProbe. And the idea there was to do preliminary design level geotech of all the stages as best we could, and then use that to better refine where we wanted to focus our investigation for detailed design. So stage 4, 5, and 6 went to those individuals. And in general, when you do a geotech program, it always takes a few months to get mobilization and permits, 6 to 8 months for the field work, maybe 1 to 2 months for draft submission of deliverables. So these were in the order of 10 months to 12 months to get this work done. And the budgets for these were in the order of $750,000 to almost $3 million. So these were pretty big individual phases. And in general, when you do these kind of programs, you get your factual data reports, subsurface models, your design reports to help the consultants, hydro-G reports, environmental site assessments we did as well, and excess soil management plans and environmental management plans. So it's your typical suite of stuff that you would do for a tunnel. Right now, I'm going to bounce to Google Earth. Can everybody see Google Earth?
Yes, we can see it.
Great. So this was just kind of my ad hoc way of keeping track of what we were doing and where and why, but it ended up being a pretty useful database for tracking stuff during construction and seeing what information we had. So you can see the tunnels here with their various colors, and each of these is a borehole that was done. So you click on it, tells you what phase it was in, the name, when it was drilled, whether there's a monitoring well, what the bedrock elevation is. So a lot of really good information. All right, let's go back to the presentation. And finally, I promise I'm almost done talking about geotech. Remember how I said the bedrock valley along the Don River kind of goes up and down and up and down? We really, really focused on that area because we just wanted to quantify it. So I'll talk right at the bottom here for the Inner Harbor West Tunnel, which for sure looked like it was going to cross that valley. And we wanted to make sure that we knew the bottom of the valley within some length running north-south in case the alignment had to change. This here is a pretty old map of contours that was developed by some Ontario mining company, and it kind of gives an idea of where that valley is right there. Although we didn't want to rely solely on this, but it does help. But an even older set of information came from the Crosstown Treated Water Tunnel, which was built almost 100 years ago now. They too encountered that valley. And in fact, it's funny that they drilled a borehole right at the edge and then another right at the edge. Of course, they didn't know there was a valley. They even drew top of rock connected between the two. You can see it. And then they subsequently erased it once they found the valley and drew the rock coming down. I don't know how they found out what it was. And maybe they probed through the roof of the tunnel, which doesn't sound very smart to me considering you're next to a lake. But either way, they found the base of the valley as best as they could. And we had a pretty good idea that it was in this area. And since we knew the tunnel alignment was going to be generally here, although it could move up and down a little bit, we peppered the area with 14 top of rock boreholes spaced out about 50 meters apart to try to get a 3-dimensional understanding of what that valley looks like. And we left a few monitoring wells in here. And we consulted a few experts on ground improvement at depth, like jet grouting and stuff like that. Just plotting those contour lines on top from the mining map, they line pretty good actually. And showing you that we tried as best as we could to keep them within the city-owned property just so we could get the information a little bit faster than getting permission from others. And this is what we ended up with, at least through the center line of the tunnel. The 3D model is something else. And you can see we found the valley pretty much exactly where we thought it was. And you can see where our proposed pre-design of the tunnel is. So it was going to skirt along the bottom of the valley. So of course, future detailed designers of the Inner Harbor West Tunnel would have to evaluate this information and judge for themselves how they wanted to either change the tunnel alignment or do some kind of ground improvement in this area. Okay, great. So enough about geotech. Let's talk about hydraulic design. So a key feature of the stage 1 Coxwell Bypass Tunnel and the stage 4 Inner Harbor West Tunnel is capturing and storing stormwater and CSOs. We already talked about that. Well, how do you do that? This little graphic here shows the general direction of flow through an existing sewer. The idea here is that flow would be allowed through this new chamber, right, to get to where it needs to go, but it'd be prevented from backflowing. These little flap gates here would close in case of a flooding condition in the lake or wherever. So when a 1 in 1 year storm is anticipated, the real-time control would tell these gates to close and the flow would be diverted. It'd go through this trash rack under a few gates and whatever, and then it would be directed to a tangential vortex drop. What is a tangential vortex drop? Well, the idea here is you can't just drop flow 50 meters down into a tunnel. You're going to draw too much air. It's going to be a lot of force coming down with it. So these computational fluid dynamic models done by Black and Veatch shows what's happening. The idea is to get the flow somewhat, I wouldn't say laminar, but to get it somewhat in a state that's predictable. And as you can see at the cross section of this chamber up at the top, you see how it narrows right before it gets to this. That narrowing causes it to speed up. And as it speeds up, it tends to go around this drop in a vortex. And that helps prevent it drawing so much air down below. And when it gets down below, it hits what's called the deaeration chamber. And the idea there is any air it does draw down, it pops right back up this air shaft. That way the tunnel isn't full of a ton of air getting pressurized all over the place as the flow is sloshing in and out from all of these connections that are to be built. And you can see here what's called an adit tunnel. Well, this deaeration tunnel is based on the Milwaukee tunnel system and removes most of the air. And then you don't need it to go all the way to the tunnel. It needs to be a certain length to help remove the air. And then you just need to get the flow to the tunnel. So this adit tunnel is just big enough to get the flow into the invert of the Coxwell Bypass Tunnel. And the idea here is to direct all the flow eventually to shafts, which help control the geysering. But some shafts have sewers right next to them. And you're not going to drill a tiny little drop shaft and vortex drop next to it. So you need to kind of convey that through the shaft. Well, how do you do that? Again, you can't drop flow 50 meters deep. So you use what's called a baffle drop structure. And to try and figure out whether this is going to work or not, Black and Veatch RVA did some physical modeling at, I think, 1 to 10 Froude scale. And these confirm the suitability of this design that was developed and determining whether the benching and the baffles actually made sense. And down below, still talking about hydraulics specifically, the gradient of the tunnel is 0.15%. And that helps maximize sediment transport while maintaining subcritical flow conditions. And sediment's going to be deposited during large rainfall events, but it's going to be remobilized during the more numerous low flow events. And doing an analysis of the typical year's rainfall showed that the Coxwell Bypass Tunnel actually is going to be broadly self-cleaning at an average sediment depth in the order of maybe like 2%. Okay, so let's talk about tunnel design. As I said earlier, the Coxwell Bypass Tunnel starts here and it goes in a big C, although we call this the Inner Harbor East Tunnel. I'm just going to call this the Coxwell Bypass Tunnel. Generally, it follows the city right-of-way, which helps reduce the impacts to other properties, and it's just generally what you would do. But you might see that the bypass that it's helping this existing Coxwell line, the bypass, looks like it's going pretty far out of the way. You'd say, why don't you just tunnel up Coxwell? Well, because we're not just trying to bypass this, we're trying to capture the flows that are outfalling into the Don River and Inner Harbor. And the way you do that is by going right next to them. If you just ran a tunnel up Coxwell, how would you connect these outfalls, right? So it has to go near them. So that's why it runs along here until it gets to Bayview. Then it runs up Bayview, which keeps those drop shafts and adit tunnels not super long. It starts at Ashbridges Bay, which is the lowest invert of the entire tunnel, runs to the Keating Rail Yard, crosses the Don River, runs up to what's called the BB1 shaft site or shaft 3. These are called shaft 1, 2, 3, 4, 5. You might have noticed this if you ever drive along the viaduct. You might have noticed the big construction site there. That's the Coxwell Bypass. That's one of the shafts. It then sweeps from there all the way to the North Toronto Treatment Plant and then over to Coxwell Ravine Park. In general, the alignment is, as I said, almost 100% through shale. I mean, there may or may not be minor little valleys that are encountered, but we'll talk a little bit later about the selection of the TBM and how to manage that. But in general, it's through shale of the Georgian Bay Formation. And as we said, it's at a 1.5% slope with a storage capacity of 500,000 cubic meters. And the lowest tunnel invert has about 20 meters of soil and 40 meters of bedrock cover. So the preferred tunnel construction methodology was a single pass system, which looks like this. A single pass is when the tunnel boring machine, or the TBM, lines the tunnel behind it. So you can't really back it up. And the precast tunnel lining is actually erected inside of a protective shield. Depending on the other features of your TBM, you can operate with pressure at the cutting head to help manage certain challenging subsurface conditions, or you can convert the TBM to facilitate mixed face tunneling where you're transitioning from rock to soft ground. There's lots of fun things you can do with a single pass system. But there's also a two-pass tunnel. This is from the East Bayfront Tunnel. And the idea there is to leave the rock exposed, but to support the obvert to help manage what's called overbreak, because the obvert gets overstressed due to the stress relief. It kind of has to flow around the tunnel and you get crushing at the top here and gravity wants to pull it down. So you manage the overbreak and then you come back later and line the tunnel. This has been used many, many times in the city. So this is the two-pass system. And as I said earlier, it's known for some time that there's time-dependent deformation or swelling in the Georgian Bay Shale. And for a project of this size, we really needed to confirm the past measured values and make sure that it wasn't going to impact the single pass preferred method. So the Georgian Bay Shale, it swells upon stress relief and exposure to fresh water. And this graph, it's just a general graph, but it shows on the left, if you don't apply a pressure to the rock, you just cut it and let it swell, it's going to swell to a certain amount. But as soon as you start pushing against the rock, it swells less and less and less and less until it doesn't swell at all. However, it's going to be really hard to apply that kind of suppression pressure. Usually when you're designing a single pass tunnel lining and you fill the annulus with grout, it's going to provide some kind of semi-confinement. And that means that the rock is going to actually be pushing on your liner. So we needed to figure out how much is it pushing on the liner, depending on when it's installed, and whether that pressure on the liner is going to be able to be accommodated by the liner, what kind of design needs to go into that liner to take that load. And part of the geotech program had Golder do a fairly fancy analysis of the tunnel and shaft lining. They call it the tunnel and shaft lining evaluation study, where we looked at all the in situ stresses and the swelling, and we tried to help determine whether or not it was going to be an issue for a single pass tunnel. And this is just one of many, many nice graphs that was produced, but you can see the idea here is that 90%, more than 90% of the convergence was going to happen prior to the installation of the precast tunnel lining, and only maybe 2 millimeters of time-dependent deformation movement would actually find its way to the tunnel lining. So this gives us a little bit of guidance on the parameters that would be used to grout around that liner. And we'll talk about the grouting a little bit later. But in general, if you're doing a one-pass tunnel lining, you're going to see higher applied swell pressures on it than if you do a two-pass lining. If you're doing a two-pass lining, you want to leave that rock exposed for at least a few log cycles. We tend to say 100 days. And once that happens, it's not going to swell much more, or at least it's not going to swell the same amount for another probably 1,000 days. So you're probably going to be okay to cast your lining. For the tunnel design, there were also a variety of crossings, one of which was, there was something like 8 or 10 crossings of the rail corridors along the route. So we needed to do finite element analysis to determine what impacts that would have. And this image shows the expected movement of this tunnel construction, where everything that's outside these colored sections was going to move less than 5 millimeters, or was anticipated to move less than 5 millimeters. And that happened to be the review level for the people we were talking, the stakeholders we were talking to. And so as you can see, the construction here wasn't really going to impact anything at grade, and this is all overburden here, and down below is the rock. But we also had to demonstrate that the loading from the rail lines would not damage the tunnel. It's all well and good if the tunnel doesn't, impact the rail, but it goes the opposite way, right? So we did another finite element analysis to look at what impacts the rail loading would have. And this image shows ground movement expected from the rail loading, and everything outside this colored section was expected to move less than 0.5 of a millimeter, which, you know, sub-millimeter is a funny word. You can't really say it's not going to move, who knows, but it's definitely sub-millimeter. And again, that was one of their levels that we needed to demonstrate to them that there'd be no impacts. In fact, most of the movement was in the overburden, which was to be expected. Great, so that was the tunnel design. Again, I'm broadly going over the large strokes here. There's lots of other things to talk about, and by all means ask me questions afterwards. But let's talk about shaft design now. You've seen the shafts a few times, but here they are again. These acronyms make sense to me, but forgotten why. But we just call these shaft 1, 2, 3, 4, 5 now for simplicity. Shaft IHES2B or shaft 1 is the lowest invert, and shaft CX1A or shaft 5 is the highest. And it's being constructed from shaft 1 clockwise all the way up to shaft 5. And in general, these shafts are strategically placed along the route to not only try to reduce the impact to all the properties that are around, but also to facilitate maintenance on the TBM. You don't want to tunnel 10.5 kilometers without having a chance to take a look at your cutter head. So these are placed generally, 3 kilometers apart-ish. And most of the shafts are in the order of 20 meters inner diameter, and they're about 52 meters deep on average. Now let's talk about the features of some of these shafts. We're not gonna talk about all of them, but there's a few different types of shafts, ones that are generally open and ones that have the baffles in them. So these are the structural elements. There's secant pile walls that help support the overburden, temporary secant pile walls. There's your cast in place shaft liner, your permanent shaft liner. And you have precast planks with a topping slab. Cutting in, you can see there's unreinforced benching on the bottom, which helps direct the flow from the various tunnels at each shaft. You have a conical base slab, which I'll get into a little bit later why it's conical. The precast segmental tunnel liner, of course, comes up to the edge and you gotta cast the concrete around it. And for the operational features, again, these shafts aren't just storing flow, there's operational elements to them too. There is a access hatch for stairs. So if you want to walk all the way down, you're welcome to. It's likely that they may just lower people down in a bucket, but there's that access. There's also a maintenance platform. Gives you a chance to kind of walk around the perimeter, take a look, maybe hose down the benching if you need to. And there's large scale removable access panels in case you need to get some heavy equipment in or out. Oh, sorry, I forgot to mention there's also air venting and an additional access to get to the invert. Remember, these shafts are going to be the primary location where the air that enters the system gets vented. Another interesting feature of one of the shafts was the regional flood level, and we had to address that, considering that the flood level was significantly higher than the actual top of the roof. So we had to design a flood-tight lid, and the vent, the air vent, had to be well above that flood level. Otherwise, the flood will actually flood the tunnel, and you don't want to have to treat flood water. Also, so that there isn't some kind of ugly rectangular thing sticking up, there's going to be some nice aesthetically pleasing architectural siding put on this particular shaft. Cutting a little bit further in, you can see similar features to the other shafts. There's stairs all the way down, maintenance platforms, benching. But what's interesting about this one, I think this is BB1 or shaft 3, is the baffle structure. So as I said, when you have a little sewer entering this shaft, because it happened to be right next to the shaft, you're not going to put a dedicated vortex drop next to it because that'd be a waste of money. You just send it right to the shaft, but it can't drop 50 meters all the way down. So you have these baffle structures, and that includes your baffle drop levels at different levels. And this again was strategically designed. There's air vents at each level because as it comes down, it is going to be drawing air. So you want that air to be able to leave that section. And you have what's called flow training walls to just keep the flow kind of manageable. And this was all physical model to kind of confirm the design. So those are the structural and operational features of the shaft. What about the design and construction features? Well, there's temporary works. When you build a shaft, you're not just casting or lining immediately, although in some ways you can sink shafts with permanent liners, but in this case, it was going to be kind of open shafts. So the idea was to put down in the soft ground, in the overburden, concrete secant pile walls. And that includes king piles and filler piles. And in this case, there was, say, 94 piles, and they were, keyed into the bedrock by a few meters just to make sure that any water that was in the overburden had a harder time to find its way into the shaft. And then down below, for the rock portion that you have to support while you're building your shaft, you do pattern rock bolts and welded wire mesh. So showing you what that looks like, you can see up top, this is the inside face of the secant pile wall, keyed into the bedrock. And down below is the welded wire mesh and the rock bolts. This is shaft 1, by the way, at Ashbridges Bay. This is IHES 2B. And I'll get back to it a bit later in the presentation, but this thing in the shaft here, this is actually a vertical muck conveyor, which is kind of a neat feature in this project. And just looking at the same shaft from below, I love this shot. You can see the rock bolts, the welded wire mesh, and the secant piles above. This is a very common way to have temporary works on shafts, at least in Toronto, in this type of rock. You may recall earlier I talked about the base slabs being conical. Well, these again are 50 meters deep. They're right next to the lake. They're going to have high uplift pressures on them, even though the rock is fairly impermeable. You still have to design for that pressure. And these shafts are going to be empty for the majority of their life, despite the fact that they're going to be carrying big flows and filled very high to the top when there's a 1 in 1 year storm event. They're not going to be full all the time. So we needed to design for full uplift pressures and an empty shaft. And it turns out that classic beam theory underestimates the true mechanics here. It leads to really unnecessarily thick base slabs. So we looked at domes to help optimize the design. There's true domes, and there's an inscribed dome. Looking at the finite element analysis of it, all the stuff in here is just clipped away, but it's all like super red, right? Because it's the high stress concentrations. But the purpose of this image is to show that the rectangular, it does exhibit kind of dome-ish behavior, the inscribed dome. So we just figured, let's just go with the true dome. It's not that hard to cut this kind of profile when your shaft's 20 meters in diameter. And both of these actually resulted in thinner base slabs than if a dome load transfer mechanism was ignored. And it turns out that the shale on the edge here, where the forces are being pushed into, was strong enough to take that load, despite it being kind of thinly bedded and kind of weak in the horizontal direction. It turned out to be just fine. And the actual base slab reinforcement that we put in here was a bundled 35 M bars in each direction. And I'll show you some photos later of what that looked like while it was under construction. So let's talk about the roof. That was the base slab. Let's talk about the roof. We considered various construction methods to optimize the roof design. You kind of, before you design something, you kind of have to have an idea of how they're going to build it. And it turns out that building a roof isn't super easy. I mean, you're going to have to either put a lot of false work inside the shaft, and for a 50-meter deep shaft, that's going to be really costly and not always the greatest option. So what are the other options? Well, it turns out you could use CPCI girders. That was used for the Western Beaches shaft, which is kind of going to be connected to the furthest extent of the Inner Harbor West Tunnel. So that's an option. Another option would be custom precast. Shown here is a project at the Kingsmead Road Sewage Upgrade Works in the UK. We've probably done one in Toronto, but this is the photo we have. And another option would be site cast post-tensioned members. And this is a photo of the Simcoe Street underpass. And one of our engineers kind of jokingly notes that some people probably didn't even realize this was ongoing until suddenly a bridge popped up. So there's lots of cool, interesting ways to optimize this roof for the means and methods we were anticipating. So the concepts we actually reviewed in more detail were the custom post-tension girders with a precast slab and the CPCI girders. Well, it turns out that the CPCI girders didn't work as well for the shaft roofs because of the incredibly high live loads from the floodplain. Now, there was going to be something like 12 feet of water on the roof, and the pre-stressing required to, resist that would have failed the beams in the opposite direction once that live load was taken off. So it didn't really work too well. The water loading was 3 times higher than the highway loading. So we went with something a little different. We did a hybrid precast slab and cast in place topping. So you can see here's the hybrid precast slab and then the topping on top. And that's what it looked like in the tendered drawings. And the best thing about this is once you put these precast panels down, they serve as the formwork for your topping slab. And the topping was 200 millimeters thick. This allows for removal of various panels when they need to get access. And also the topping helps provide long-term durability during the harsh Canadian winters. Another interesting feature of the shaft design was unbalanced loading. So the idea here is the rock may have major and minor stresses slightly different in either direction, but they're not super different. Typically your cast in place concrete shaft is going to have mostly compression most of its time, but every now and then you're going to have some ovaling that results in tension, and you need to kind of design for that. In this case, this is the shaft at Keating Rail Yard, shaft 2. The developers nearby, they required significant flexibility in their future design, which we were happy to try to accommodate, which included full depth excavation to rock of any size. So when you remove the overburden from one side of the shaft, you don't have a consistent pressure all the way around, and you're going to get some ovaling. Also, the stakeholder required a provision for future adjacent construction, which would result in a 30% reduction of the earth pressure in any one quadrant. So that was a fun little challenge. Also, considering that this shaft had a baffle drop in it, that was interesting to try to design for those unbalanced loads, but we managed to do it. And talking about shafts and the general construction sites, this happens to be shaft 4, just as an example. Just wanted to show you the kinds of things that went into the site plans. So you got your access road in and out, and access to the muck. Your shaft, of course, and the crane to do all the work inside the shaft. Security trailers, parking, your material storage, because there's lots of muck coming in and out, and you need to put stuff in the shaft to construct it, of course. And then you have your dewatering equipment, because there's always going to be a little bit of water coming in, and your tunnel ventilation equipment. This just gives an idea to the contractor that it's feasible to fit all the typical sizes of things within the construction compound. Okay, great. Let's talk about the precast tunnel lining, or the PCTL. This shows the tender drawing of the precast tunnel lining. In general, the intention was to have an annular space between the outside diameter of the lining and the bored rock, I'd say about 200 millimeters. And that space was to be filled with grout that would have been specifically designed to accommodate that rock swelling we were talking about and the stress relief. So this grout would crush in a controlled way to transfer the forces to the precast tunnel lining. The final precast tunnel lining design was prepared by Hatch, I believe, and manufactured by CSI Tunnel Systems in a joint venture with Forterra Precast at a local facility in Whitby. And the precast tunnel lining, the final design was 300 millimeters thick. It was a typical universal ring assembly, which has 4 rhomboidal segments and 2 45-degree trapezoidal segments. And these segments happen to be 1.8 meters in length into the page. And that length was to help facilitate longer excavation cycles and improve production. And I just want to know before I go forward that all these fancy graphics are by CSI. So thank you, CSI. The precast tunnel lining has been designed to facilitate ring builds in a turning radius of nearly 200 meters with a concrete compressive strength of 50 MPa. And it is reinforced with steel fibers to provide a minimum residual flexural strength of 3.4 MPa at L over 150. And the gaskets are designed to handle 12 bars of hydrostatic load. And as it turns out, the time-dependent deformation, the swelling of the shale that we talked about, it wasn't found to actually really increase the precast tunnel lining axial force or bending moments, which was good. This shows what it would look like in a straight drive. Although the tunnel's at an incline, this is more or less a straight drive in plan. And this is how you put the pieces together. But when you're turning, the layout changes. So we'll go back, that's straight. But when you're turning, you have to put them together in a specific way to actually achieve that radius. And you can't get super, super tight radiuses because your tunnel boring machine is 100 meters long. So there's only so many radiuses you can make work, but you don't want multiple different values for your radius. You don't want to have a radius that's 200, then 400, then 600, then 200, then 400. It makes sense to have as many straight sections as possible within reason and keep the similar type of radius to have as few unique turn diameters as possible. That makes it more simple on site for the guys to put it together. And this is CSI's manufacturing yard. They made sure to keep far ahead of tunneling production. Couldn't help myself, had to put a meme in there. But, you know, there's what, 5,300 rings, which is 32,000 segments in total. So this is a 10.5 kilometer tunnel lining. And we had to make sure that as the precast tunnel lining was being manufactured, it had somewhere to stay, but it was also being sent to site at the right time so they wouldn't have to stop their tunnel boring machine. And of course, when it shows up on site, it has to be piled in a specific way to protect the integrity of the lining, and then grabbed as need be. So all of these have tracking chips in them. They know exactly which one was manufactured when and where, and the components inside of it, where it is in the tunnel, exactly which ring. It's a cool system. All right, so now let's talk about construction update. I kind of blitzed through the design. Let's talk about construction. Oh, actually, before I get into it, I just want to say that the Coxwell Bypass Tunnel was tendered in late 2017, and it was awarded in early 2018. And construction commenced in August of 2018, and it's expected to be completed in 2024. And the total capital cost of the Coxwell Bypass Tunnel is $400 million, excluding taxes. All right, so let's go over shafts. You may recall this image. I'm not going to talk about the progress of each shaft. That would take a long, long time, but I just wanted to kind of go over it broadly. Shaft 1, 4, and 5 are fully excavated with temporary works, and shaft 3, 4, and 5 have their base slabs poured. Shaft 3 has all the walls poured. Shaft 4 is on its 5th or 6th wall lift, and shaft 5 is has its wall lifts in progress. Shaft 2 happens to have the C-camp pile installed and is currently being excavated. So moving forward, I'm just going to show you images predominantly from BB1. Now this is shaft 3, BB1. And of course, after you put all your temporary works in place and you've excavated your base shaft into the conical shape, you can jump in there. I'll note that you might notice the bars here are like orthogonal. You can also reinforce a slab with your bars radial. And that's originally how we thought it might work, but ultimately it gets really, really congested in the middle. And we just thought this might be better, and it actually worked for the design just fine. And you know you have a pretty thick base slab when you have to use a step ladder to tie the top layer of steel. And at the edge of the curve here, right on the edge, that's about 1.5 meters thick. And in the middle, it's 3 meters thick, which constitutes this as a mass pour. And we'll show you later what that looked like. But generally, for the majority of the base slabs for these shafts, the thickness ranged from about 2.5 to 3.5 meters. So for 50 meters deep, that's not super thick. For BB1, the continuous base slab pour took place on November 18th, 2019. It started at 3:30 in the morning and ended at 6:30 in the afternoon. The contractor, North Toronto Constructors, NTC, they used one stationary pump and one mobile pump. And they used 860 cubic meters of mass concrete, which is about 95 concrete trucks. And thankfully, the curing process met the specified 20-degree maximum temperature gradient across the slab and the 70-degree peak temperature requirement. So when you're doing mass concrete, you got to be really cognizant of the temperature of the concrete. It's an exothermic reaction, it heats up, and when it's really, really thick, you can have performance issues if it gets too hot or the gradient is too different within the slab. In terms of getting the bars down there for the walls, these are huge diameters, so they had to have kind of forms lined up to help tie these things, and they sent the bars down in bundles. Before I go to the next image, I just want to show you this here. These are the strand jack supports that they use to lift up and down the formwork. And once they move the panels of rebar down here, they get them in place, they make sure that there's water stops in between each joint, and they tie everything up and make sure the cover, of course, is correct against the welded wire mesh. This is what the formwork looks like for the walls. They just started at the bottom and pulled the formwork up to the top using the strand jacks. Pretty neat system. It worked really, really well. And this shows the formwork kind of hanging out below, but having formed the walls nearly to the top. The base slab, sorry, the roof slab goes on top of this, of course. And one interesting thing, I don't know if this is BB1 or TTPT, but either way, one of the shafts has this small sewer. You remember how we talked about those baffles, how a sewer was coming in and you can't just drop it 50 meters deep. So this is the opening left for the sewer, and this notch left in the wall here and here was a future connection for that wall that separates the entire baffle structure from the rest of the shaft. Okay, then starter and tail tunnels. The starter and tail tunnels, they were excavated to pretty much help assemble and launch the tunnel boring machine. However, the tail tunnel also helps facilitate a connection of the Coxwell Bypass Tunnel to the future influent pumping station. It's no good for everything to flow to this shaft if it has nowhere to go. This needs to be connected to the eventual pumping station, or integrated pumping station, I should say, that helps bring it into Ashbridges Bay and treat it. Now, NTC, the contractor, extended the length of the starter tunnel behind me in this image to 117 meters. And the tail tunnel is 74 meters. This is the starter tunnel. So they used rock support ribs, bolts, and welded wire mesh with 100 millimeters of shotcrete. This was the temporary support. And the base was finished with a mud slab, as you can see. Excavation of the starter and tail tunnels was with a road header. And the top bottom bench rock support was installed by utilizing an electric drilling unit. And then shotcrete was applied by utilizing a automated shotcrete sprayer. So fancy stuff. And I'm just going to zoom into the front of the starter tunnel now. Couldn't help myself, I had to put a photo in, but the purpose of this is to show the size of this tunnel. It's a 7.3-ish bore diameter, huge. And, you know, this could easily fit a MP40 locomotive from Metrolinx. This is a big, big tunnel. Remember, the actual inner diameter is 6.3 meters. Okay, excavated tunnel. Let's talk about the tunnel boring machine and where we are today with the TBM. NTC procured a new convertible tunnel boring machine, lovingly named Donnie, I guess, Don River Central Waterfront. So it's named Donnie, and they procure that to complete the whole excavation of the tunnel. Now, this TBM is actually designed to operate in open mode during rock excavation, and it's going to use a muck ring, a belt conveyor, to pull the rock from the chamber at the front there. But it also has a capability of operating in closed mode, and that's with the excavation controlled through the earth pressure balance method, up to 6 bar design pressure. And the earth pressure balance mode, it utilizes a continuous flighted auger screw conveyor, and that helps remove the muck from the excavation chamber. So you may recall we were talking about 1-pass, 2-pass methods. This is a 1-pass method. So they erect the precast tunnel lining inside the shield, and as the tunnel boring machine pushes off the lining that was installed behind it, the precast tunnel lining inside of it gets exposed to the bore, and they grout the interface. Since you can't back this machine up because it's pushing off the precast tunnel lining, it needed to be able to deal with challenging ground conditions such as a buried valley, and that can be dealt with through the closed mode, the earth pressure balance mode. Just zooming in a bit, just to show you how long this thing is, it's 115 meters when it's fully assembled and over 1,000 tons. And it was also manufactured by Love Sons in China. Of course, it needed to come here, so it was delivered on a big ship, very nice looking ship, and brought over in pieces. And this kind of shows you what it looked like taking it to the loading dock. Of course, we got streetcars everywhere, and those wires are not super high up, and these pieces are huge. So a very careful coordination needed to be done to make sure that every single piece got to site safely without impacting anyone or anything. Thank goodness. Of course, once everything got delivered to site, it needed to be unwrapped and assembled in the starter and tail tunnel. And this image here just gives you an idea of what the cutter head looked like as it was being lifted vertical. Down below, these are some photos of them putting together it piece by piece. This is an incredibly complicated machine here. And once it was fully assembled well, not fully assembled, but once certain pieces were assembled, they were able to slowly start moving it forward up to the end of the starter tunnel. Now, usually these TBMs would thrust off of a precast tunnel lining that's right behind it, but there wasn't any yet in the starter tunnel, so it has to thrust off of something. So they installed a thrust frame behind the trailing shield where the concrete blocks that you see here and steel rails would be used to thrust. And of course, based on the chainage and where the tunnel boring machine was, they would lower whichever precast tunnel lining rings were necessary at that location down through that shaft. And once it got to the bottom, it was put on a rubber tire vehicle, or RTVs, lots of fun acronyms. And those are used to transport the precast tunnel lining to the tunnel boring machine heading. And I think NTC noted that this was the first project in Ontario to use RTVs in lieu of conventional means and methods. Of course, once the precast tunnel lining gets to where it's going, it needs to be fed to the front of the tunnel boring machine. And in this case, vacuum loaders and unloaders were used. And once it gets to the front, they had to orient it in the right location and lift it into place. So this is going to show a quick video of what that looks like. And don't forget, there's about 32,000 of these to do. So it needs to be done right. Once they get into a groove and they know what they're doing, they can just blitz forward on it. It's very impressive how quickly they can put these together. And once they're in place and all bolted up, you want to grout through the injection ports. And that makes sure that the interface between the outside of the precast tunnel lining is in contact with the rock. All right, so I've shown you this photo before, but I'll show it again. This is what it looks like when multiple completed rings are assembled. And within the tunnel, you need to have your ventilation. It just so happens to be up at the top right here. It's hidden, but we'll talk about it a little bit more later. This is the continuous muck conveyor. It takes all the muck from the entire length of the tunnel back to shaft 1. And on the left is your pedestrian walkway and a bunch of utilities as necessary to operate your TBM. And in terms of the current location of the tunnel boring machine, as of November 18th, because that's when I finished looking, the tunnel boring machine is at, I guess, this bridge here, Eastern. And that's about 3 kilometers of tunneling. And there's 7.3 remaining to go. And NTC noted to me that the best day of tunneling was 40.5 meters in 2 10-hour shifts, which is pretty impressive considering that the bore is like 7.3-ish meters. So that's pretty darn good production. Also, just one final thing about the tunnel is the continuous muck conveyor. Now, everything from the entire 10.5 kilometer tunnel is going to come all the way down to this shaft at Ashbridges Bay. Once it gets into the shaft, it has to come up. So this whole system, it's actually a pretty complicated system. It has a horizontal discharge conveyor. It has an incline conveyor, a vertical shaft conveyor, and a tunnel conveyor system. All these things work together to bring the muck up, over, and then deposited down on the far side of the site. Another view of it right here. And this, just sits here until it's ready to get hauled off to wherever it's going. And just to give you an idea of how big those piles are, there is a person for scale. All right, so that's the presentation. We talked about the overview, the Don River Central Waterfront project, what it is, why it's being done. It's got 5 stages, about $3 billion over 20-ish years. And the purpose is to improve water quality in the Don River and the Inner Harbor. And right now, the Coxwell Bypass Tunnel is just one of 5 stages of the entire system. So looking ahead, even though preliminary design was completed for all 5 stages and stage 1 construction is underway, there's still detailed design left to be done for the Inner Harbor West, and it's been awarded recently, and then the future other stages. So overall, just the whole planning and execution of this Don River Central Waterfront program, I think it's a pretty landmark achievement for the City of Toronto, and it really properly demonstrates the city's commitment to eliminate CSOs, improve aquatic habitat in the lake, and delist Toronto's waterfront as an area of concern.